So now that we have some of the derivative patterns practiced a little bit, hopefully, we're going to go on now to the product and quotient rule that are on this page here. And I think the best way is just to jump right into it. So let's say we have this function, x squared times sine of x, and I'm actually going to change this to an h here. You'll see why in a moment. And we're going to use this over here, what's called the product rule. So when you're adding and subtracting functions, the derivative distributes. So that's this property here. If you're adding or subtracting, then the derivative distributes. However, if you're multiplying functions, like in this case, then you have to use the product rule to deal with multiplication. And so this is how we would do that, this is where recognizing what your pieces are here. So going just back to objects, if you can recognize that this is like a triangle times a square, that would be great. If you can recognize that the triangle here is a power function and that the square here is the sine function, then you're going to know what derivative patterns to go to. So I do think very important, you can look at a function. So for instance, when you first saw x squared sine x, did you think that this is a power function times a trig function? That would be a good way to think about this. Because what we're going to do is break this into a function times a function. And then we're going to identify what we are saying is f and g. So if we go back to our equation here, we're going to say f is the power series function. And we're going to say that g is the trig function. And this is our first step for product and quotient, actually, is to look at the functions you have, identify what pattern they are. Is it a constant, power, exponential, log, trig? And then we're going to break that apart into an f and g, or whatever letters you like, but the book does like to use f and g's. And now that we have our f and g here, we're going to take their derivatives. So we're going to want the derivative of x squared. So that's our power function. And the derivative of x squared is 2x. And then we're going to want the derivative of g and the derivative of sine. Trig function here, derivative of sine is cosine. And these are all four pieces that we will always need for doing product and quotient. So what we have here, let's write this out, is we're going to say this function h is two functions being multiplied together. And we're going to say those functions are x squared and sine x. And then we're going to take the derivative of both sides. Now on the left side here, the derivative, the h, can just slot up right here into the operator notation. Usually the function notation is dropped, just to say dh over dx there. And on the right side, this is where we have to deal with now, how do we take the derivative of two functions being multiplied? And that's where the product rule comes in. Math is mathematicians have already figured out how to do this for us. By the way, if you do want to see a proof of the product quotient and chain, I do have something I can send you on that I've written up for people who are a little bit more interested in that. But what we find from the product rule is that the derivative of two functions being multiplied will be the function f times the derivative of g plus the derivative of f times g. And that's what's written down here as the product rule here under derivative properties. And I do want to say, because people teach this differently, I myself like to keep letters alphabetical. So you see I have FG here, FG. But then the derivatives switch position. So in this first term, the derivative is second. But in the second term, the derivative is first. Some people like having the derivative always second. So if you do look at other material or read other things, some people also like to write this then as fg prime plus gf prime. So they like to have the derivatives always second. However you want to remember it, it's up to you. Both these ways equal each other. I don't want to get too confusing about things, so I'm just going to stick with the alphabetical way. And so we want the derivative of h. And now we have our answer on how to do that. The derivative of h with respect to x will be f times the derivative of g plus the derivative of f times g. So let's do that. So we're saying the derivative of h is f, which is x squared, times the derivative of g, which is cosine x, plus the derivative of f, which is 2x, times g, which is sine x. And that's our answer. So here is our function, and here is the derivative. Now at this point, how would you know this is the answer? And there's not much you can do except double check your work. There is something you can try to do with graphing though. And so I want to show this here. Here is what the original function looks like. This is x squared sine of x. And now remember, the derivative is a measure of how steep the function is. So right at my cursor here, right here, you can see the function is going up, so it has a positive slope. The derivative is positive here because the function is sloping up. And if we look over here at my cursor, now the function is sloping down, which means the derivative is negative. So the derivative is positive when the function's sloping up, because that's a positive slope. And the derivative is negative when the function slopes down, because that's a negative slope. And between positive and negative is 0. And a 0 slope occurs at the very top. And so what does that mean? Well, at the very top of this function, when the derivative is 0, means our answer better give a derivative of 0 right here. In other words, our derivative better have an x-intercept right here where we expect the function to have 0 slope. So what you would look for to check, to give yourself some confidence that your answer is right, is you graph the original function and look for peaks. So here's a peak and here's a valley. Wherever there's a peak and a valley, the derivative has to have an x-intercept. And also right here at the origin, I like to call this a plateau. Notice the function here just momentarily goes flat. This is also a derivative of 0 because the slope is horizontal right here. And I'm going to put up here now the derivative. So the red line is the function, and the derivative is the blue line. Now I know that's pretty confusing looking here, but remember the red line is the function, and at the very top here of the function, notice the blue line has an x-intercept. And that's what we would expect, because the derivative has to be 0 when the function has 0 slope. And so we can see the blue line does have an x-intercept at this peak. We can see the blue line also has an x-intercept where the function was a plateau, a derivative of 0. And if we go to this valley right here, the red line, you can see the blue line has an x-intercept there because the derivative is 0. And everywhere this blue line intersects with the x-axis means the red line must have a peak or a valley. And we're going to get into much more with this on the derivative into the future here. But as for now, this is really the only means you have to check your work, to give you some confidence that your answer is right. Besides, double checking to make sure you didn't make any mistakes. You could graph the function and graph the derivative, and then look to see, does the derivative have x-intercepts where the original function has peaks, valleys, or these plateaus? So let's take a look at another example. E to the x times natural log of x. And I'm calling this f again, but let me call this h because I don't want you to get confused with the f over here in the product and quotient rule. So the first thing you should do is identify what functions are we dealing with. So we have an exponential function times a log function. So we know for property patterns, we're using the exponential pattern and the log pattern. Also, identifying the functions allows us to split this up then so that we can use the product rule. So we're going to look at this function and acknowledge that it's a function f times some other function we're going to call g. And we're just going to write those definitions out here. So we're going to say f is e to the x, and we're saying g is natural log of x. That's what we're saying there. And now to complete the product and quotient, we will need the derivatives here. So the derivative of e is always itself. And the derivative of g, the derivative of natural log of x, is 1 over x. And these are our 4 pieces. We have f and g defined from the information given. We then take the derivatives of f and g, and now we're ready to go and use the product rule. So let's look. I do have the product rule on the right side here. So the product rule says the function f times the derivative of g, so times the derivative of g plus the derivative of f times g. And that's our answer. Now, it is usually pretty nice thinking, I guess, if you do factor out the greatest common factor. So we see both of these have a greatest common factor of e to the x. So that is something we could factor out of this to get us our final best looking answer. So here's what that looks graphically. Here's the original function. Now notice the original function has no hills or valleys. There's no part where it curves up, it hits a top, and then curves down. This function is always everywhere increasing. So there's no hills, there's no valleys, there's no plateaus, which means our prediction is the derivative will have no x-intercept. The derivative can only have an x-intercept if the original function has a hill, a valley, or a plateau. This has none of that. And sure enough, the blue line, which is the derivative, has no x-intercept. And again, at this point, now does this prove your answer's right? It doesn't. This is only evidence. But at this point, this is the best you can do to check that your answer at least looks right. So we'll check out another one. Cotangent x plus x cosine x. What is this derivative? And I keep using f here. Let me change that back to an h here quick. And I want to be a little bit more thorough on this one just to be clear. So we're going to take the derivative of both sides. So the left side will be our derivative notation then. And we're taking the derivative of everything on the right, and the derivative distributes. And so we're taking the derivative of these two things individually. Now, if we look to the right here, what is the derivative of cotangent? Well, that's actually one of our patterns. The derivative of cotangent is minus cosecant squared. So this derivative here is minus cosecant squared. And that derivative is done. So the product rule is actually on this part right here. And I want to focus on that part because this is where we're going to have to do the product rule. So again, what we're doing is we're recognizing what functions we have. We have a power function times a trig function. And we're going to call the power function f, and we're going to call the trig function g. Now, it doesn't matter which you call f and g, it doesn't. But once you call it f, you better continually call it f through your entire problem. You got to be consistent. And then we're just going to simply write that down. So we're saying f is x. And we're going to say g is cosine x. That's what we're going to say. Those are the two functions we are identifying as being this other function h. And then once we have those definitions, we will then take their derivatives. And the derivative of x is 1. And the derivative of cosine is minus sine. And again, it's just all from the derivative patterns over here. So x is a power function. And here's the derivative of sine. or I mean, the derivative of cosine is minus sine. And here's our information. And this information then allows us to complete the product rule. So we know this derivative, looking at the product rule, it's going to be f times g prime plus f prime, which is 1, times g. And that's our answer. That's our derivative. And sure, maybe we'd want to clean it up slightly, because the minus sign we could pull out here, and we really don't need the parentheses. And that is our answer for the derivative of x cosine x. And now we have our final answer for h, because we know the derivative now of x cosine x is up here. And then there is our final answer. I just want to copy the original function here real quick. So here's our original function h, and here is our derivative. And the purpose of this one that I wanted to show you is that this was an example of having just a straight derivative pattern plus a product rule. So this information can come in all shapes and sizes. So let's check out another one. So here we have x times 2 raised to the x times secant. And I wrote f again. Let me change that to an h. Such a hard habit to break, that f. So what you should be able to do here is identify the functions that we have here. So you want to identify, you've got a power function, you've got an exponential function, and you've got a trig function. And they're all being multiplied together. Now, the product rule only says f times g, but we have 3 functions here, and we still define that as an f times g. Now, it's up to you on how you define f and g next. That's completely up to you. It doesn't matter how you define things, as long as you're consistent through your work, you'll be okay. But I'm going to define f in this case to be x times 2 raised to the x. And then I'm going to define g to be the secant. Now, you could have defined g to be 2x secant. You could have done that. And now our next thing to do here is to get the derivatives. And I'm going to do the secant one first, because we already have that derivative pattern here on the right. The derivative of secant is secant tangent. So we're almost done, except we need the derivative of f. And the derivative of f, notice, is another product rule. So this problem is an example of 2 product rules. So what we're going to do is do another product rule here for f. So I'm just going to pick some new letters here. I'll just say M and N, I guess. And then we have to define what those are going to be. So I'll say M is the first function. That's a power function. And I'll say M is the exponential function. And then, once we have our definitions here, we take the derivative. So the derivative of x is 1. And the derivative of an exponential is always itself times the natural log of the base. And so here's our information to find the derivative of f. So the derivative of f, looking down here back at the product rule. Now, of course, I'm using M and N's now because we already use f and g's. So the product rule says we first do m times the derivative of n. And then plus the derivative of m. The derivative of m is 1 times n. And n is 2 to the x. And that is our derivative then for f that we were trying to figure out up above. Now I can go back up here and paste that in. Now, of course, we're not done yet because we still ultimately want the derivative of h. And now the derivative of h, looking at the product rule, it's going to be f, which is x 2 to the x, times the derivative of g, which is secant x tangent x, plus the derivative of f, which is what we just figured out. So the derivative of f, whoops, mistake there. I'm missing a 2 right here. So it's x natural log of 2 times 2 raised to the x. And that mistake got pasted in here then. So going back to h prime, we're at plus. So the derivative of f. Here's the derivative of f. Plug all that in. And this is going to be multiplied. So we're going to have to use a parentheses around that. That's all going to be multiplied by g, which is secant x. And now, there's nothing that says your answer has to look pretty, but there it is. We could do a little bit of gathering terms here. Since all the terms, so there's a 2x here, 2 raised to the x here, 2 raised to the x here, so all the terms have a 2 raised to the x that we could factor out. And all the terms have a secant x. And so we could factor that out as well. for our final answer. We're just not going to get to make look any nicer. So there is something I hope you're realizing by seeing this example, is that things have just upped ante here. I think hopefully you're seeing by this that things are all of a sudden going to get a lot more dense looking. So there's a lot going on here. And this is only a double product. All we did was do the product rule twice, and things can get ugly pretty quick. So really important to try to keep your bookkeeping, like I did in this example here. Try to keep everything separate. Try to label things clearly. Good bookkeeping is a good practice to make sure that you're handling all your information correctly. So that is product rule. Let's check out what happens when we have division. And I'm never going to get rid of that F there. So if we have division, we would then go to the quotient rule down here. And we're going to do the same thing as we did with product. Instead of recognizing this as F times G, we're going to recognize this as F divided by G. And we're going to do the same thing by defining then what F and G are. So we're saying F is 2x plus 5, and we're saying G is 3x minus 4. And the next thing we're going to do is get those derivatives. So we can do the derivative term by term because it distributes. So the derivative of 2x is 2. And the derivative of a constant is 0. Going to G, term by term, the derivative of 3x is 3. And the derivative of a constant is 0. Now again, this is something you should know from algebra. Remember, the derivative tells us the slope. What is the slope of a linear function 2x plus 5? Well, you know the slope is 2. And that's what the derivative is telling you. So now that we have that information, we will plug it into the quotient rule. And so I want to write this out again. So we're going to say our function x is composed of two functions, f divided by g. And then we're going to take the derivative of both sides. Now on the left side, this h just slots up right here into the notation, and then the parentheses are usually dropped just because it's cumbersome. And then here's our statement. The derivative of h is the derivative of this ratio. And if you look down on the bottom here, mathematicians have figured this out for us. Again, if you are interested in this proof, I have one written up to send out to you if you're interested. Are you going to want to memorize these? Absolutely. Product and chain. Again, everything I have on this right page, you should burn into your brain. So here is our quotient rule. And here is our information. So we will just plug it in. So what did we figure out f prime was? We figured out f prime is 2. What's g? Well, g is 3x minus 4. We have to use a parentheses there to make sure things distribute. Then we have minus f. Well, what is f? 2x plus 5. And then what is g prime? G prime is 3. And then finally, what is just g? Well, regular old g is 3x minus 4. And that's what we have from plugging our information into the quotient rule. And then we'll clean that up. So if we look at the numerator here, I'm just going to write this separately actually here. If we look in the numerator, we would have 6x minus 8 minus 6x, because remember there's a minus and a 3 over here. So it's minus 3 times 2x, get us minus 6x, and a minus 3 times 5 to get us a minus 15. And very rarely will you want to distribute the denominator, I mean here. Usually you just want to keep it here as x squared, because it's already factored that way. And now if we look at the numerator, 6x minus 6x will subtract out. And minus 8 minus 15 is minus 23. And that's our derivative, all cleaned up and ready to go. So here's our original function. There's our original function. And then going through the quotient rule, we found the derivative. Check out another example. This f, I have it pasted into all my example problems. So what are we going to do now? Imagine this is a homework problem or a test problem. You're going to look at this. What do you want to identify? What things should happen in your brain? What should happen in your brain is you should recognize the numerator is a power function. The denominator is a trig function. There's division of a function in a function, which means we need quotient rule. All three of those things you should identify. So we've identified this is a function divided by a function, and that we need quotient rule. And so the next thing we do is then explicitly state what our functions are. So we're going to say f is x cubed. And we're going to say g is cosecant. So that's explicitly what we're saying. And then once we do that, we will need these derivatives. So just do them next is a good step. So the derivative of x cubed, remember the 3 drops down, subtract 1 from the exponent. There's our answer. And then we want the derivative of cosecant. So it's one of the patterns over here to the right. The derivative of cosecant is minus cosecant cotangent. So now that we have all our pieces, we will plug them in to the quotient rule. So what is the derivative of f? It's 3x squared. What is g? It's cosecant. What is f? F is x cubed. And what is the derivative of g? Well, the derivative of g is minus cosecant cotangent. And this is all divided by g squared. And what is g? It's cosecant. And so that's what we get from plugging in all our information. And then we'll do our best to clean this up. So a minus times a minus is a positive. And if we look here, this has x squared. So this term has 2 x's. This term has 3 x's. So we can factor out at least 2 of those x's. And this term has a cosecant, and this term has a cosecant. And so we can factor that out as well. And then notice, now we have a cosecant here that will divide out one of these cosecants. And we don't need this parentheses really anymore, so I'll just get rid of it. And there's our final cleaned up answer. So we'll try another one, but I do want to stress again, hopefully you're seeing that things are getting more mathematically intense compared to test 1. So here we have another function. And what should you identify? You should identify that we got a square divided by a circle. We have a trig function divided by a log function. And because we have a function divided by a function, means we have to use quotient rule. So we're going to identify this as our trig function divided by our log function. And then we're going to explicitly state that by saying f is sine x and g is log base 3 of x. And once we explicitly state that, we will then need those derivatives to do the quotient rule. And so we'll take those derivatives. And the derivative of sine, in case you haven't memorized these yet, probably not, it's only been one day, but the derivative of sine, cosine, and the derivative of log is always 1 over x. The derivative of log, always 1 over x. Except in the denominator, you'll have this factor of natural log of the base. And the base in this case was 3. And there's our information. And let me just grab a copy of the quotient rule real quick up here. Because I think that works pretty good, just showing you how to plug it in. And so the first thing we do is plug in the derivative of f, which is cosine x. And then we multiply this by g, which is log base 3 of x. And then we do minus f. F is sine x. And then we multiply this by the derivative of g. And the derivative of g is 1 over natural log 3 times x. And this is all divided by g squared, where g is log base 3. And that's what it looks like when we plug in everything. And that looks pretty messy, and it's going to stay pretty messy. Because the only thing we can really do is slot this sign up in the numerator here is really all we can do. And that's our final answer. Nothing in math that says your final answer has to look nice. So let's check out one more. There it is. What should you do first? You should identify what functions we have here. And I just want to state this again, that the way I see this is very similar to just object recognition. I literally see this as like a triangle times a square, all divided by a circle. I see these parts. I see there's a power function here. I see, whoops, that's a 2, should be an x. I see there's an exponential function here. And I see there's a trig function here. I see these 3 pieces, which I strongly encourage you to do as well, so that you know what you're dealing with and you know the derivative patterns you're going to need to use, and also that you're identifying this is a function divided by a function, which means quotient. These are all things that I think are crucial to identifying to make sure you're proceeding correctly. Now, how we define f and g next is up to you. It's not going to matter as long as you're consistent throughout your problem. But I'm going to say here, f is x e to the x. And I'm going to say g, and I'm going to say g here is cotangent. Now, once we have our definitions, we then need their derivatives to plug them into the quotient rule. Now, if we look at the derivative of f, now what do you see? Hopefully you see the derivative of f requires the product rule. The derivative of f is a power function times an exponential function. A function times a function requires product rule. So this is something I'm going to hold off for a moment because we're going to need to do separate work to do that product rule there. But the derivative of cotangent is something we can look at our patterns for. And the derivative of cotangent is minus cosecant squared. So we have these 3 pieces. And now we need to look again at f because we need that derivative. So I'm going to say f is a combination of 2 functions again, m times n. And then I'm going to explicitly state then what I mean by m and n. I'm saying m is x and n is e to the x. Once we have those declarations made, we then take their derivatives. So the derivative of x is 1. And the derivative of e to the x is always itself. And there's our information. And now we will plug this into the product rule to get the derivative for f. So looking at the product rule, in your brain, try to switch these f and g's to m's and n's. So the product rule here is saying, what is m? Well, m is x. And then it says, we'll multiply by the derivative of n. Well, the derivative of n is e to the x. And looking at the product, so we add the derivative of m. The derivative of m is 1. And when we multiply that times n, and n is e to the x. And there is our derivative for f. Now that we have that derivative for f, we can plug it back in to our information up here to finish off the original problem. And let me grab the, I should have had this ready to go, maybe. I like using that formula there and just pasting stuff in it. Works pretty good. So, f, the first thing we want to plug in. So now we're doing the derivative of h, which is a quotient rule. So the first thing we plug in is the derivative of f. And we'll need some parentheses there since the derivative of f has multiple terms. And next it says plug in g. G is cotangent x. And then f. What is f? F is x e to the x. And then finally, well, not almost finally, but the derivative of g is minus cosecant squared x. And now finally, we'll plug in g into the denominator. G is cotangent. And so this is what it looks like when we plug all our information in. And then we'll do our best to clean things up. So the minus and the minus here is a positive. Because that minus is gone, we don't need this parentheses anymore. And if we look at the first term, this e to the x can be factored out here. And by doing that, hopefully you can see there's an e to the x in the first term. There's an e to the x in the second term, which means we can factor an e to the x out of both of those. And that's the best we can do. That's our final answer. So let me just show again. Here's the original function. And here's its derivative. So in closing here, I'm a realist person. And I try to balance that with trying not to be, or at least sounding negative about things or trying to scare you, because that's never my intent here. It's just to tell you what the reality is. And the reality is things are going to get harder. And I'm convinced all of you have a human brain, and I'm convinced the human brain can understand this. It may take time. It may take practice. I do consider math a skill, and like any other skill, you get better at it by practicing. So I'm strongly encouraging you to practice this. Develop the skill. I'm going to keep my same schedule that I will sit on my computer through the week, around 11 to 7 or so, just sitting on my email, seeing who's going to ask questions. And please ask me questions. It's absolutely imperative, top priority, that you can learn this skill. And when we talk about the chain rule in the next lecture, we will then get to full difficulty level. So there's still another step of complexity here. So again, I'm not trying to scare you. I'm convinced you can all understand and do this, but it is going to take practice. And prepare yourselves for the next video when we talk about the chain rule, because the chain rule will then allow us to do very complicated expressions. And I will talk to you in that video.